and then his PhD in at MIT Mechanical Engineering. So his focus of his research is basically how do we design soft materials with extreme properties. And his talk of today is about fracture of polymer networks with diverse topological defects. So whenever you're ready, Shaoting, you can share your screen.
Great. Thank you, Bianca, for your kind introduction.
Shaoting, probably you can restart the recording.
I already restarted the recording.
Oh, okay.
Yeah. I think it's a recording, right? Did you see
I
a
think
recording?
the on. Yeah.
Yeah, because I stopped first, then I restart again.
Oh, I see. Okay.
Okay, so the current is the recording, right? So as long as the current is recording, I think everything is fine. Okay. Thank you very much. Thank you, Bianca, for your kind introduction. And I'd like to thank all the EASF committee who have spent your precious time and efforts to organize and maintain this platform. I have been moderating several episodes in the last 2 seasons, and it will be my great honor to present some of my research in today's EASF forum. So I changed the title and some of the contents of my today's talk slightly, and hope it can match the audience with different backgrounds. So my name is Shaoting Lin. I'm currently working as a post-associate in the Department of Mechanical Engineering. Today, I would like to focus on bioinspired design of fatigue-resistant hydrogels for applications in biomedical engineering. So in the past 6 years, I have been working on designing extreme properties of soft materials to form a long-term, high-efficacy, multimodal interfaces and convergences between humans and machines. And the human tissues and the organs are mostly soft, wet, and bioactive, while machines are commonly hard, dry, and biologically inert. So interfacing humans and the machine has been extremely challenging due to their fundamentally contradictory properties. And the softer materials, particularly hydrogels, due to their low softness, high water content, and the active responsiveness, represent ideal material candidates to merge the hard, dry, non-living machine with the soft, wet living human body. So there are several killing challenges that limit the practical deployment of the softer materials. For instance, conventional hydrogels are usually mechanically brittle. The first question is, how can we design high-performing hydrogels that can be comparable to biological tissues such as tendon, muscle, and ligament? And the second question lies in the difficulty of fabricating large-scale three-dimensional 3D material structures with multi-functionalities. Real biological tissues typically have the hierarchical and heterogeneous structure across landscapes. Can we closely mimic such kind of structure through advanced manufacturing process? And lastly, what will be the real impacts that are inaccessible by existing conventional technologies? Well, these are basically the 3 quests through the journey of my PhD work. One long-lasting interest in the field of soft materials is how to impart synthetic soft materials with combinational tissue-like properties. So specifically, the properties refer to mechanical and physical properties that are comparable to those of biological tissues, including toughness, resilience, adhesiveness, and electrical or ionic conductivity. So far, it won't be actually a big surprise to achieve one or these properties for short-term laboratory demonstrations. But the key challenge is really how to maintain these properties under long-term dynamic loading conditions, which is essential for longevity of applications of soft material. So here is one example. So people are able to make super tough hydrogel adhesions to diverse engineering solids. And once the hydrogel adherent experiences cyclic peeling loading, it will gradually detach from the substrate over cyclic loading. So with that being said, the so-called tough hydrogel or tough hydrogel adhesion suffers the issue of mechanical reliability. And in contrast, the biological tissues are able to maintain their robustness over millions of cycles per year. For example, tendon is a connective tissue to bridge the rigid bone with soft muscle. It can maintain high toughness over 1,000 Joule/m² over millions of cycles. And such remarkable fatigue-resistant properties really attributed to 2 physical reasonings. The first one is the hierarchical structure of the aligned fibers across landscape so that it can enable simultaneous stiffening of multiple polymers. And beyond that, the presence of the ordered structure of collagen fibrils is also known to be the key factor. So naturally, we are curious for two perspectives. So the first one is what will be the impact of nanocrystals on fatigue resistance of synthetic hydrogels? And the second one is how to engineer such a hierarchical aligned fibrous structure in synthetic hydrogels. And to answer the first question, I performed a systematic fatigue study on semi-crystalline hydrogels. I first characterized the average distance between neighboring crystalline domains and the average size of the nanocrystals in the series samples with controlled growth of nanocrystal domains. And our data shows that the substantial crystal domains can remarkably increase the fatigue resistance of hydrogels. So this is the first experimental evidence suggesting the important role of the nanocrystals on fatigue properties of synthetic hydrogels. The second question is how to engineer hierarchical aligned fibrous structures in synthetic hydrogels. The first technique is about mechanical training. So what I found is after this cyclic mechanical training in a water bath, the original random fibers inside the hydrogel can be trained to align towards the training direction. And the water acts like the plasticizer to enable the reforming process of the hydrogen bonds. And we find that such aligned fibers or fibrils can effectively pin the fatigue crack propagation. We later further leverage the power of 3D printing to engineer the microfibers closely mimicking the multi-scale structure design in biologic tissues. So far, we are able to achieve multi-ink, large-scale, high-resolution three-dimensional applications. And depending on the application, you can further incorporate functional components such as living sensors and conductors for use inspired modern technologies. And finally, our fatigue-resistant hydrogel successfully demonstrated one practical application as the edible hydrogel pills. So here is the working mechanism. So the patient first orally takes one hydrogel pill in the size of 1 centimeter. And once the hydrogel reaches the stomach, it swells rapidly by 60 to 100 times volume and resides in the stomach. And due to its high fatigue resistance, it can not only sustain the long-term mechanical disruption forces generated by the stomach, but also withstand the strong acidic chemical erosive environment. So we further collaborated with bioengineers to demonstrate its capability in a large animal model. So the hydrogel pill can safely stay in a pig model for up to 30 days. We also show its promising potential as a platform for long-term psychological signal monitoring. So here is the temperature profile to monitor the dietary activity for 30 days. And the patent of this work was recently licensed by a startup company, Millicat System. So they are really eager for retention unit to host their electronics chips in the stomach. So we are excited to see our material innovation and its practical translation are making progress toward our long-term goal of using inspired technologies. On the other hand, these progresses mask one basic fundamental problem, how to quantify or what physically determines the ability of a software material to resist its fatigue crack propagation. So current efforts have been mostly focused on mechanical characterization of bulk samples at macroscopic levels. Ruobin is the pioneer initiating this field, or force spectroscopy to characterize single chain properties at nanometer scale. So my interest is to understand the fatigue of software materials at the network level through combined experimental and theoretical efforts. So one classical understanding on fatigue software materials dates back to the Lake-Thomas model, which defines the intrinsic fraction energy, or alternatively fatigue threshold, as one physical quantity to characterize the energy required to initiate crack extension per unity area under fatigue loading. So physically, the value of this energy is equal to the energy required to fracture a single polymer chain times the number of chains per unity area of the crack surface. The model has been very successful and widely used even nowadays, in the sense that it can be generally applicable to different kinds of polymers, hydrogels, and elastomers. But recent studies manifest several limitations of this model. So first of all, Lake-Thomas model underestimates the intrinsic fraction energy by a few times, and currently there's no model to theoretically explain this underestimation yet. And the second, the Lake-Thomas model does not consider the effect of topological defects, which are inevitably present in real polymer networks. And the real polymer networks contain various topological defects such as cyclic loops, dangling chains, polymer entanglements, chain length heterogeneity, and functionality heterogeneity. So here the chain length defines as the number of monomers between the neighboring cross-linkers. And the functionality is defined as the number of chains connected to one cross-linker. And if one end of the chain becomes inactive, it basically introduces one dangling chain. And the number of the inactive chains connected to one cross-linker actually defines the order of the dangling chains. So for example, we term this one as the first order dangling chain. And we term this defect as the second order dangling chain. And if all the chains are active, they still can actually present in the form defects in the form of cyclic loops. So as we show here. And the number of the cross-linkers inside the loop determines the order of the cyclic loops. So what we schematically illustrate here basically is a secondary loop. And for highly concentrated or interpenetrating network, the neighboring chains can feel interactions with each other, giving the defect in the form of molecular entanglements. Due to the limited time of today's talk, I will be mostly focused on cyclic loops and dangling chains. And we'll leave molecular entanglements and other defects for post-discussion if time allows. Let me start with an ideal polymer network. An ideal polymer network means a polymer network has a uniform chain length, a uniform functionality, and is free of defects. And once crack propagates, it will first relax the energy stored in the fractured polymer chains. And for the neighboring chains at adjacent layer, although they are not fractured, their elastic deformation still provides the relaxed energy as an additional energetic contribution to drive the crack propagation. So here we calculated the energy stored at the different layers. And as we show here, the relaxed energy is delocalized for multiple layers. And qualitatively, this is consistent with the recent experimental observation based on mechanical chemistry published by Professor Creighton. And we further calculate the energy relaxed by all the layers. So here is the expression. So which actually eventually give a finite value with a prefactor of F divided by F minus 2. So F is the functionality of the polymer network. So here is actually U chain actually denotes the pristine value based on the Lake-Thomas predictions. And the energy contribution by the neighboring chains can be significant, especially for ideal polymer network with low functionalities. So for example, for a tetraarm ideal network with functionality of 4, the intrinsic fracture energy predicted by our model is 2 times the Lake-Thomas model's prediction. We next calculate the energy relaxed by the chain affected by the second loop and affected by first order dangling chain as 2 representative examples. And both energies are higher than that of an ideal polymer chain, which actually indicates the toughening effect due to the presence of defects. Here we introduce a quantity gamma x to quantify the toughening effect due to the presence of defect x. And the gamma x is a dimensionless parameter greater than or equal to 1. So if it is ideal on F at ideal polymer chain, it's basically just equal to 1. Otherwise, it's greater than 1. We further quantify the number of densities of different types of chains due to the presence of defects. The presence of a second order loop will not only introduce any, so the presence of the second order loops, first of all, it does not introduce any inactive chains. But secondly, it will introduce affected polymer chains. What's the difference is for the dangling chains, it will introduce both inactive chains and affected chains. So here's one example. So the presence of the one second order loop basically actually makes the one original chain become longer, but actually do not introduce additional new active chains. So alternatively, in other words, all the arms of this polymer basically is inactive in some sense. given the number of the defects in the system, we eventually will generally calculate 3 types of defects. One is the density of the inactive chains. The other is the density of affected chains. And the last one is the density of unaffected ideal chains. And indeed, the summation of the density of the 3 types of chains is equal to 1 constant value because of the chain number conservation in the system. So far, we have identified the fracture effectiveness of each type of chain. And we're also able to quantify the number densities of different type of polymer chains. With that, we are able to calculate the intrinsic fracture energy of a polymer network, which is basically a mean value of energy considering the effect from the different chains. So here is the general expression. So the first term actually describes the toughening effect due to the effectively longer chains, since the fracture effectiveness, as I mentioned, is always greater or equal to 1. And the second term is always negative, which describes the weakening effect due to the presence of inactive chains. Next, we will perform experimental to validate this quite actually elegant theoretical framework. We specifically select the AB type tetraon polymer networks for experimental validation. The material system has several advantages. So first, it can intrinsically eliminate first order, third order, and the other odd order loop defects. Secondly, we set the polymer concentration at 50 grams per liter, which is below its overlap concentration. So there will be no polymer molecular entanglements in the system. We're trying to make the system as clear as possible in the current stage. Third, we check people's simulation result to ensure our polymer concentration is above a threshold value below which actually the cyclic loops can be introduced in the system. So currently, actually, we basically neglect the presence of cyclic loops. And the ultimate system is a relatively clean material platform, which contains various orders of dangling chains. And we further adjust one actually material experimental parameter, basically is the hydrolysis time, to allow the MHS ester to degrade over time, and so that the reaction efficiency of the system can be readily tuned. So basically, if you let the system stored for a longer time, the reaction efficiency of the polymers will degrade accordingly. So here we use the measure the shear modulus to calibrate the reaction efficiency. And for the reason that the model for predicting shear modulus has been well established and validated in the field. And given the identified reaction efficiency, we can further actually calculate the intrinsic fracture energy based on the amount of the macromers with various orders of dangling chain in the systems. So as we show in the left plot, our model quantitatively capture the reported experimental results. And one additional note we would like to highlight is we find that the fracture energy and the fatigue threshold is an ideal of an ideal polymer network are the same. And even after introducing these the various density of defects, its fracture energy and the fatigue threshold still maintain approximately the same. This estimation is also independent of the loading rate. We check this conclusion validated at a different loading rates. So this evidence further suggests the promising potential of using the material system to study other material fundamental properties of softer materials. So to summarize, so we learned the design strategy from nature inspiration. We provide the first experimental evidence to show the impact of nanocrystals on fatigue resistance in synthetic hydrogels. We also provide multiple routes to engineer hierarchical aligned fiber structure, including mechanical training and 3D printing. We also successfully demonstrated one application as ingestible hydrogel pills for long-term psychological signal monitoring. And beyond the material design and fabrication, we're also trying to push the fundamental understanding on fatigue of softer materials. We propose a defect network fracture model to quantify the impact of topological defects. And from experimental side, intense efforts currently have been mostly focused on randomly cross-linked networks. So here we show the potential using ideal network as a material platform with well-controlled architectures and the defects.